professors, teachers, and fellow students. I'm glad to give a presentation on our topic, night school. We are from Shatin Secondary School. Our registration number is 51078. To begin with, let me simply describe the problem. Consider a night move in the n times n chessboard. The night moves just like the one in international chess as the PowerPoint shows. However, the chessboard we talk about throughout this presentation is the modified one. That is, the knight can also pass through the edge and return to the chessboard. On the screen, the black circle represents the knight. The knight can move to the places outside the region, represented by the violet circle. The knight will then return back to the chessboard with the corresponding position as shown by the red circle. Same goes for other moves. We define closed tour as, first, the knight starts at any square. After moving n square steps, it returns to its starting point. Second, every square should only be visited once. Our objectives are, first, to determine any closed tour for positive integer n. Second, to find out the number of closed tours can be complete if closed tour exists. Through observation, it is quite complicated to find closed tour by the original moves. So we want to simplify the generating set S through two steps. First, we want to reduce the number of moves from 8 directions to 2 which are linearly independent. For a linearly independent order pair, their determinant should be relatively prime with n. Therefore, the determinants of elements in S can only be 3, 4, or 5. When n is relatively prime with 3, we choose directions 1, 2, and 2, 1 as their determinant is 3. We choose 2, -1, and 2, 1 for cases which n is relatively prime with 4. And we choose 2, -1, and 1, 2 for cases which n is relatively prime with 5. Second, we would like to transform S to a simpler form through an isomorphism. Let phi be a function with the following properties. First, phi x1, y1 equals to 1, 0. Second, phi x2, y2 equals to 0, 1. Third, phi a plus b equals to phi a plus phi b, which means phi is a homomorphism. From above, we choose x1, y1 equals to 2, -1, and x2, y2 equals to 2, 1 for n equals to 3, which means phi 2, -1 equals to 1, 0, and phi 2, 1 equals to 0, 1. Then phi is an isomorphism. Therefore, transformation can be done on S to change the element to 1, 0, 0, 1. The diagram shows the closed tour before and after S undergo transformation. At the bottom, here, the arrows represent the moves of the knight before taking transformation, here, and after transformation. The upper number in the box represents the knight takes how many steps to reach that square, and the number at the bottom represents the coordinates of the square. From the right diagram here, we find that it can be constructed as follows. The green lines represent the edges by 1, 0. The vertex at the right here will return back to the left after moving with 1, 0, which forms a cycle. The white lines represent the edges by 1, 0, 1. Unlike the green lines, it forms a cycle too. Then the diagram is a Cayley graph. Our objective of finding a closed tour for a knight is equivalent to finding a Hamiltonian cycle in this Cayley graph, set n square 1, 0, 0, 1. The answer is positive because of this theorem. As a result, there exist closed tours for each positive integer n except multiples of 30. Since the determinants of elements in S are not relatively prime with multiples of 30, then S cannot undergo transformation. Therefore, we cannot determine the existence of Hamiltonian cycle through this method. Therefore, the first objective is done. In order to count the number of ways for the knight to complete a closed tour, we define elements of S10 as A and 01 as B. Also, P, Q, R, and S is the number of A inverse, B, and B inverse respectively. To avoid subtraction equal to E, and under the rules as shown without loss of generality, the only possible combinations for P, Q, R, S are 6030, 4122, and 3330. For case 1, 6030, the only possible cycle type is shown here, which means interchanging A and A inverse, B and B inverse, also A and B will result other Hamiltonian cycles. On the other hand, the cycle is also harmonic if its starting move is changed without changing the sequence as the PowerPoint shown. As a result, the total number of closed tours for case 1 is 24. For case 2, 4122, the possible cycle type is shown here. It is still a Hamiltonian cycle if it is changed in a similar way as case 1. Therefore, the total number of closed tours for case 2 is 72. For case 3, it is not possible to construct a cycle, so there is no closed tour. Therefore, the total number of ways for the knight to complete a closed tour is 96, of course, for n equals to 3. To conclude, for a n times n chessboard for all n except multiples of 30, there exists closed tour. For chessboard 3 times 3, there is 96 different ways to complete a closed tour. After submitting the report, we have generalized the existence of Hamiltonian cycle. For an n times n square chessboard, consider a super knight, moves with the steps shown here. That means R and S can be any integers. Here are some examples. The sufficient condition for the existence of Hamiltonian cycle is that n is relatively prime to either one of the determinants here. Also, we have found the sufficient conditions of a rectangular chessboard to have a Hamiltonian cycle. That is, M is a multiple of n, and provided that the generating set S can be reduced and transformed into linearly independent directions 1, 0, and 0, 1. For the future research directions, we may consider, first, how many closed tours are there in square chessboards when n equals to 4, 5, and so on? Second, is there any method to solve the cases for n is a multiple of 30? Third, is there any general solution for the number of closed tours in a n times n chessboard? Fourth, is there any closed tour for m times n chessboard for different values of m and n? That's all of our presentation. Thank you.